All right, welcome to Module 12. We're going to talk about electrical safety, and it's a personal protection type of situation. There's many different aspects of electrical safety, whether you apply it to electric power systems in high voltage environments or you apply it at home. Electrical safety is something to be aware of. Electricity is invisible, and knowing where the hazards are ahead of time is really the purpose of electrical safety. And we're going to talk about some of those hazards here in this module. So in this module, the objectives are discuss the essential safety aspects of electrical power systems, explain what is meant by ground potential rise, explain the meaning of touch and step potentials, describe the uses and applications of personal protective equipment, referred to commonly as PPE. Discuss electrical safety around the home, and discuss electromagnetic fields around power lines. These are the areas that we're going to be focused on here in this module. Okay, starting with substation grounding. Substations have a ground grid underneath the gravel. I pointed that out in an earlier module about the substation ground grid. There's copper wire buried 18 inches basically below the surface of the ground, and that ground grid ties all of the structural steel together, the control building, the fence, everything metal around the substation, the equipment, the dead tank circuit breakers, and the metal around transformers, all attaches to the ground grid. Having everything tied together as a ground grid creates what's known as an equal potential. Is zone of equal potential. Everything you touch inside the substation, the breakers and the structural steel and what you're standing on and a switching platform and a control building are all connected together to form what is referred to as a equal potential. Now, when a fault happens in a substation or a lightning strike hits in a substation, that energy is dissipated throughout that ground grid and dissipated into the earth. Into the conductive earth. If it's a fault in a substation, then the energy is going to go back to the sources through the earth, and in some cases back through neutral and static wires, but most of that energy is going to go back to the sources through the earth. And that's what the ground grid is basically allowing to happen. So here's a picture of a substation with a ground grid with a power fault hitting these, and then letting all this substation energy fault energy get dissipated into the earth, and it's really a current that's going back to the sources. Okay, and when that energy gets distributed out to the sources, it creates what's referred to as a ground potential rise. So here's a substation, here's the ground grid, there's a fence around it, there's a control building, and let's say there's a fault in a transformer, maybe 120 kV transformer bushing just flashed over to ground, and we have a line to ground fault, and that energy is going into the ground grid, into the earth, and creating what's referred to as a ground potential rise. And maybe that ground potential rise is 20,000 volts, because the grid resistance when you measure it turns out to be 1 ohm, and then you have a 20,000 amp fault. There's a few other numbers going like square root of 2 and peak, asymmetrical, whatever. But the bottom line is, if you have essentially a 15,000 amp fault in a 1 ohm ground grid, you end up with not 15 kV, but even greater than that because of the asymmetrical peak and because of some other reactance to resistance ratios causes it to be even higher. But bottom line is, let's say you have a 20,000 volt ground potential rise around the substation. The idea is, in the substation, everything you touch is going to be 20,000 volts. So everything is basically safe. You're standing on 20,000, you're touching 20,000. The difference of potential is essentially zero. It's like flying in an airplane at 20,000 feet. Everything is relative. It's okay. It's normal. That's what happens in a substation under a fault. The whole ground grid rises in potential, but you don't know it, but you're at a high voltage potential. But that voltage potential, that ground grid, dissipates into the earth and spreads out over a distance. Spreads out, that becomes known as the zone of influence. This is the zone around the substation where the voltage drops to, typically defined as the 300 volt point is the parameter. They're not always in circles, depending on the soil conditions. It could be whatever shape it happens to be. But just get the idea of a substation having a ground potential rise. Everything in the substation is kind of like at a plateau, and it just fades away. Okay, and that's what a GPR is all about. Okay, when you have a ground potential rise, that creates conditions for touch and step potentials. So here's the substation with its ground potential rise, okay, and it fades away. And if you were next to the substation, you might be at this potential, touching the fence, having a difference of potential, just being outside the substation, touching the fence. You could have a difference of potential because the potential is dropping, and that could be hazardous. So most substations, all your modern substations, maybe dating back to 20, 25 years, somewhere in there, old, normally put a ground wire around the outside of the fence, 3 feet out, a meter out, so that it's tied into the ground grid, so a person standing outside the fence could be touching the fence just as if they were inside standing on the ground grid touching the fence. So there's this equal potential zone around. But once you get away from that, the potential drops. So here it's dropping, okay? So you have what's called touch potential. If you're standing where the voltage in the earth is dropping and you're touching one object at one voltage, standing barefoot would be the worst case, with a difference of potential, you'd have a touch potential issue. Also, if you were barefoot and you were standing away from there, there's going to be a difference potential just between your feet. Okay, so as you're walking away from here, there could be a difference of potential. That's why people say when there's a car accident, when you get out of the car, you don't want to touch the ground and the car at the same time, because if there's a wire, a high voltage electrical wire on the car, the 4 tires act as insulators. So the metal car is at a high voltage and the earth is grounded. So when you get out of the car and you touch the car and the ground and you're shorting out the rubber tire insulators, you can have a potential across you that could be harmful, it could actually be fatal. Okay? And also you hear about, oh, then you're supposed to jump out of the car. That's right. If you jump out of the car, you're at one potential, going to another potential, okay, without touching the car. Now you're on the ground potential. And when you walk away, you either take baby steps or you hop because of step potential. I mean, it might sound crazy, it might sound, way out there, but this is reality in power systems. You have touch and step potentials, okay? When lightning hits, some type of a pole going up, it'll send out energy, and that energy can have, drops, and that's why cows standing near a tree, for example, if a tree gets hit with lightning and the energy goes out, cows have the 4 legs, and they're at different potentials. That could kill cows. That's kind of what happens is step potential. So there's touch potential, step potential. In a substation, you try to have equal potential so that you don't have the issues of difference of potentials. This is all about electrical safety. So when you have a fault, a ground potential rise, there are situations where you have touch and step potentials. And, there's a lot you can go into on electrical safety. Okay, so we're going to just keep it at this high level for now. Okay, now here's where we get into the personal protective equipment, PPE. This is where we're talking about rubber gloves and rubber blankets and those types of rubber goods to act as an insulator. Okay, so the first glove here is actually a cloth. It's just a cloth, cotton cloth that you put on just to kind of keep your hands dry when you put them into the insulating glove. And this insulating glove is usually tested at 30 kV, 20 to 30 kV RMS. So you can bare hand 12 kV, and you tested the glove for higher than that. And then you have a protective leather glove that slips over the insulating glove, and you work with these big gloves and you're trying to do work with it, but you're protected 20,000 volt type isolation. Then you can actually touch energized lines, or if a line might be de-energized, but if it accidentally became energized, you're already protected. So this is a form of personal protective equipment, rubber gloves. Here are more personal protective equipment products. Here's a rubber blanket so that you can stand on it, or you can cover something up with a rubber blanket, also good with the same insulation level, or a rubber mat, a little sturdier material that you can stand on and not get damaged by small rocks or those types of things. It gives you insulation from the grounded earth. Okay, and then there's rubber boots that are rated for 20,000 volts or so that you can actually walk on step potential if there happens to be any, or prepare yourself in case you're walking across and a fault happened, and you're now insulated from a ground potential rise or a step potential. So these are more rubber goods, more personal protective equipment that's used in the power industry for safety. Okay, and this slide talks about the different types of maintenance and how it's performed in a system. Here we have a transmission bucket that's insulated bucket, and these guys are working on changing out insulator strings on a transmission line. And the transmission line is de-energized, and you can tell by the jumpers that are hanging over here. There's actually ground jumpers that are connected inside here that on the lines, you can barely see them there, but it's grounding out. You can see there's insulators here, but there's no insulators on this cross arm because they're changing them out. So on the far side of the tower is a three-phase power line, and on the near side of the tower is a separate three-phase power line, which they are re-insulating. So here they're using an insulated bucket, and they're also grounding the line, and they're trying to provide electrical safety, changing out the insulators. In this case, these men are using an insulated hot stick to connect a ground jumper, a 4-aught jumper it looks like, going down, connecting the ground grid to the what used to be energized conductor. The circuit breaker has been opened, the air disconnect switches were open to give a visual disconnect, and then they can put a jumper and actually ground out the bus work so they can do maintenance on it. Okay, in this particular slide here, happens to be me, doing a bare hand live line connection there. And what it is that's a live 345 kV transmission line, and I'm in a conductive suit, conductive hood, conductive gloves, conductive boots, everything conductive. Okay, and I'm sitting on an insulated ladder, about 150 feet in the air. And I shimmy out on that ladder, and then that ladder gets swung into the energized side of an insulator string. And I'm taking the insulated gloves, and I got a lanyard there with the clamp on it that I'm actually clamping onto the energized conductor, and that's putting me at 345 kV, just like the line. So at that point, there's no sparks, no arcs, no nothing. I'm equal potential. When you're at equal potential, it's kind of like standing on, if you take the positive side of a battery and just be all over that positive side, no problem. You can be all over the negative side, no problem. You just don't want to go across hot and ground. So long as you stay at equal potential with one side or the other, you're safe. And that's what bare hand live line maintenance is all about. So a lot of transmission crews use bare hand live line maintenance, so they don't have to take the transmission line out of service for maintenance. You can do everything. You can change insulator strings out. You can do all kinds of things keeping the line energized. But it's a different type of safety. Here's where we're using conduction and insulation in order to provide safety. So this is total grounding, equal potential. This is insulation. And this is a combination of the two. Insulation being on fiberglass ladders, and conduction being at equal potential with the high voltage line. So, just an overview of electrical safety in the power system. Okay, Switching and tagging is a very important part of electrical safety in the power industry. You hear about switching and tagging. What that's all about is if these folks here, this gentleman here has got a hot stick and he wants to operate one of the disconnect switches around that breaker. And the switching and tagging is through system control. There's a procedure that is for each thing. If you want to take a circuit breaker out of service, you go through a procedure. What do? Well, you got to stop all automatic reclosing. You got to open up a certain circuit breaker, then disconnect switches, and then verify they're open and locked open and everything's safe. Now you can go in and actually put grounds on and short out in case an accidental energization occurred. And all this is written out, and you go through communications and you make sure that you're able to do the proper switching and the tagging saying this equipment is out of service, there's maintenance on it. In system control, that might be on the computer system, the electronic tagging saying you cannot operate this breaker. We have people on reporting to it. The people that are reporting to it, when they're done, then they have to go through this reverse of the switching orders and remove tags and those types of things. It's a very elaborate process. I'm just trying to give you an overview of what that's all about. But if you were to do some major maintenance in a substation, those switching orders could be pages long, and it could take hours to totally get the situation ready for someone to even go in and work on a piece of equipment. It's all about switching and tagging, and this is just a quick, high-level overview of what that is and what that means. Okay, don't forget electrical safety at home. That's a big issue. At home, even though it's 120 volts, 240 in some cases, it's still just as lethal as high voltage environments. Yeah, you can be killed with 120 volts. Okay, so you have to be careful that if you have electrical wires that are exposed, and if it touches water, that could make the conductive water. Water is basically non-conductive when it comes out of the sky as rain or in snow before it melts. But when it melts and it comes down into the rivers and you have all the contaminants and all the minerals and everything that the water picks up on, that makes water conductive. And when you have conductive water, it's just as bad as having wire. The human very vulnerable to electric current. So if we create current flowing through our body, it could be very harmful. So make sure that all your electrical appliances and the cords and all the wires are not exposed. You have proper grounds. When it comes to those old type non-polarized plugs that have the same size and that you can plug either way, those are hazards. It's always good to have polarized, make sure everything's grounded properly, and eliminate the potential for touch and step potentials. Eliminate that possibility so we don't have any problems at home. Now, these ground fault circuit interrupters, these are designed to trip at a differential current of 5 milliamps, which means the current going out on the hot wire must equal the current coming back on the ground on the neutral wire within 5 milliamps, so that you don't have a differential condition, because that little relay, if you will, assumes that if the differential is greater than 5 milliamps, that extra current is going through a human body, going through an alternate ground path, and it's not coming back on the neutral, so that breaker trips. So it's all about safety. Safety in a home is so much more improved now than it was many years ago, thanks to the National Electric Code and getting things up to date. It's very important that you have safety at home. It's just as vulnerable as safety in the power industry. This slide talks about electrical safety in a different way. This is electromagnetic fields. What's going on with electromagnetic fields? Is there a problem with electric fields or magnetic fields with results in cancer or anything else going on? Well, many years ago there were several studies on electric fields and magnetic fields, but electric fields, I actually was involved in some of that work, and it was back in the early 80s, and we were measuring the electric field at the edge of right-of-ways and the electric field under conductors, and and comparing that to things like electric field off of electric blankets and wires in homes, or what are you exposed to? Well, the electric fields around the house, at the edge of right-of-ways, the center of right-of-ways, are all well below the Department of Energy's standards on exposure. And so there really wasn't anything found to be a hazard with electric fields on power lines. So then the focus moved over to magnetic fields, and looking to see if magnetic fields have anything to do with health issues or those types of things. And there too, there was no true conclusive evidence that the magnetic fields had any strengths that came close to exceeding the exposure levels that humans can be exposed to. And if there were, people working around big, large motors might have magnetic field issues or those types of things. And actually, I think it's kind of funny because I watch over the years that it got to the point where it's not magnetic fields. There was an industry out there that was selling magnets to put on as bracelets or around your neck because it made you feel better. Or you put magnets around your back if you had a sore back. They're thinking the magnetic fields actually help you. So, there's different things like that. But, all the evidence that I've come across and I've studied and I was a part of shows that the magnetic fields, electric fields around power lines with the types of clearances and what we use today, does not affect the health. And I'm a believer of that. Okay. Even though there's people might think there's a power line, in electromagnetic fields and cancer and those things, there's no true evidence that I'm aware of that shows that there's any real correlation. However, if it's in a person's mind thinking that way, then by all means, follow that path that makes you feel the best. But when it comes to underground, that's what this other one here, magnetic fields from center of right-of-way and underground systems to overhead. And the basics theory here with electric and magnetic fields is, as you recall, when there's a current flowing through a conductor, it creates rings of magnetic field. Okay, that's fine. But the electric field always has to be perpendicular to the surfaces. So if you have electric field here at a certain high voltage, it's got to end up being perpendicular to the ground. So you have a straight electric field line here, and then as you go away, it's 90 degrees all the time. And the magnetic field has to be 90 degrees with the electric field. So these circles all get skewed based on making sure that we got 90 degrees on the magnetic field meeting the electric field. And you kind of get some kind of crazy lines like this. You can have computers draw it perfectly, but that is the idea behind electromagnetic fields. Okay, to summarize this module on electrical safety, okay, we talked about the essential safety aspects of electric power systems. We covered basically at a high level the different types of safety issues. I do want to point out too that this picture here is using the rubber goods, all of the insulation, all the insulating materials. That line is operating energized. It's a distribution line. They've got the blankets, and they call that hose, covering up the conductors. And all of that equipment is covering up so that you can do surgery, in a sense, in one exposed area. And with the rubber gloves and arms and all the protective equipment around you, it's designed so that if you accidentally touch something, you're going to be okay. It's not really designed to, let's hang on to this now and let's just, hold on to this energized wire. It's really, we're going to work on this energized piece, we're going to get that work done and move on. I want to, make that clear. So that's working with PPE and insulated equipment. Okay, we talked about ground potential rise. When there's a fault, a lightning strike, it causes the energy to go into the earth, and that current that's going into the earth times the earth resistivity, the resistance of the earth. Current times resistance is a voltage, and that voltage creates a ground potential rise. We talked about touch and step potentials that occur because of a ground potential rise. And where do they occur? We talked about, equal potential and step potential, walking away from an energized structure. Okay, this is, that was under a fault condition where energy is being dissipated. Those are where touch and step potentials occur. We talked about personal protective equipment, the rubber insulating goods that's used to protect someone from touch and step potentials. And we talked about electrical safety around the home. Keep in mind, touch and step potentials do occur around the home. If somebody were washing their car barefoot and water all around, and they reach over and grab a vacuum cleaner that's plugged in, and if that vacuum cleaner cord had a frayed insulation on it, and the hot wire was touching the water, that water could become energized, and a person touching the vacuum cleaner metal case, which is grounded, could create a current condition that's flowing from the vacuum cleaner to the person as a short circuit, and that person could be seriously hurt. And if they fall, that's a good thing. It breaks the connection. So, you just got to be careful about, electrical safety around the home as well. Then we talked about electromagnetic fields around power lines. We talked about, how the current and the voltage fields, are produced, and the levels that, how they're shown to not be harmful, and those types of things. So that talks about, electrical safety in power systems, and it's a good overview, and there's a whole lot of training and education that goes on to be able to do what these gentlemen are doing in this picture. It takes a lot of knowledge and wherewithal to be able to understand the touch and step potentials and how to deal with, electrical safety in power systems.